Thank you for joining us today for our discussion of ROHM Semiconductor's low voltage and high voltage GaN solutions featuring our EcoGaN and nanopulse control technologies. As most of you know, gallium nitride has become an important part of the power electronics industry. But as we will discuss, even within GaN technology, there is not a one-size-fits-all solution. That is why we will be providing details on ROHM's low and high voltage GaN solutions. So let's take a look at our agenda for today's webinar. I'm going to start with a brief overview of ROHM's power product lineup. Then we will look in detail at our broad portfolio of low voltage 150 volt products before finishing up with a similar detailed review of our high voltage 650 volt products. So let's get started. One of ROHM's goals as a company is to be a complete power solutions provider for our customers. This includes individual power devices, power integrated circuits, power modules, and key passive devices. As you can see in the upper left, ROHM has power transistors and diodes built in 3 different technologies: silicon carbide, silicon, and our newest offering highlighted in yellow, gallium nitride, built on our proprietary EcoGaN process. By offering power devices in all 3 semiconductor technologies, customers can select the best technology to meet their requirements for power, voltage, current, switching frequency, and cost. Moving over to the middle of this slide, we have our power IC products. ROHM's goal here is to be your one-stop shop for power products by offering power management ICs, gate drivers, and standard ICs. Again, highlighted in yellow here in the middle are ROHM's latest ICs in support of our GaN technology offerings: the DC-to-DC controller for GaN and the gate driver for GaN. Throughout this talk today, we'll be focusing on the 3 new GaN-related power products shown on this slide. But before we move on to that discussion, let's take a look at where GaN fits in the overall space for power applications. This can be a really helpful slide in understanding how the many different power semiconductor technologies complement each other. This can help you make the best selection of process technology to meet your application needs. The graph has switching frequency on the x-axis and switching power on the y-axis. On the graph, we'll start at the left. You can see IGBTs at the far left with the tan background color. These are limited to only very low switching frequencies, but are able to handle extremely high switching power. Silicon MOSFETs occupy the bottom middle of the graph, highlighted with a green background. They definitely support higher switching frequencies than IGBTs, but not as much switching power. Silicon superjunction MOSFETs are often ideal for low-cost, high-volume applications that do not have the extreme performance requirements that necessitate moving to one of the other technologies. In the blue shading, directly above silicon is silicon carbide. Like GaN, silicon carbide is being used much more often these days, with the advances in electrification for EVs, renewable energy, industrial power, and much more. SiC supports both extremely high powers and relatively high switching frequencies. Finally, on our graph at the lower right are the GaN high electron mobility transistors. These support medium power levels similar to silicon MOSFETs, but at much higher switching frequencies that reach into the megahertz range. As we will discuss in more detail later in this presentation, the higher switching frequencies provide opportunities to reduce the size of power solutions and increase power density. This makes them ideal for power supplies in data center servers, telecom base stations, and even EVs. ROHM Semiconductor has power products using all 4 of these technologies, so this slide is a good reference to help you get started in identifying the right technology to meet your application needs. Of course, if you need help selecting the best technology, our team at ROHM is happy to help. With that background established, we will now dig into the main part of today's discussion. We'll start with an overview of our 150 volt low voltage GaN solutions and then dive into some discrete products. For this part of today's webinar, we will examine 3 key product families from ROHM Semiconductor that provide a total solution: the DC-to-DC controllers, the gate drivers, and the EcoGaN power devices. One of the key advantages of working with ROHM is that we can provide this complete application solution, something our competitors cannot do. Every product on this slide is a new offering from ROHM. The DC-to-DC controllers on the left include our nanopulse control that supports high-speed switching. In the middle are our single-channel and half-bridge gate drivers. And finally on the right are the 150 volt low-voltage discrete EcoGaN transistors. In the following slides, we will be working back from right to left to discuss these new products in more detail. This slide demonstrates one of the major advantages of ROHM's 150 volt EcoGaN transistors. These systems typically have a nominal gate drive of 5 volts. To maximize efficiency, the goal is to switch on as quickly as possible. However, due to the inherent inductance and capacitances of these systems, high-speed switching will result in an overshoot of the gate voltage. Most of these transistors have a gate-to-source voltage limit of only 6 volts. So it doesn't take much of an overshoot to result in damage, as illustrated in the red curve. As shown in the bottom left curve, the typical solution for existing products is to add an external series gate resistor to dampen the switching. However, this slows the rise time, as you can see, which reduces overall system efficiency. The ROHM 150 volt EcoGaN, shown in the blue at right, has a VGS rating of 8 volts. This is 33% higher than the typical 6 volt limit and allows the ROHM GaN power transistor to switch rapidly without worrying about gate breakdown. So, no external gate resistor is required, allowing you to maximize your system performance. There are 3 products in ROHM's EcoGaN low voltage product lineup. Each is rated for 150 volts of drain source voltage with the 8 volt rating on the gate source that I highlighted on the previous slide. They are packaged in a mold resin package that includes a copper clip electrical connection for low parasitic inductance. In the lower left corner, you can see the specification differences between our 3 models. You can select between 5, 10, and 20 amp currents and drain source resistances from 40 down to 7 milliohms. The higher current versions naturally have the lowest series resistance. These characteristics make them ideal for data centers, base stations, industrial LiDAR, and more. One of the other advantages of selecting GaN products from ROHM Semiconductor is our vertically integrated supply chain, with many of our manufacturing operations performed in-house at our facilities in Japan. From the manufacturing of epi substrates through the front-end GaN fab operations and through final packaging, ROHM provides a high-quality, stable supply for our GaN products. Now we're going to move on to discuss ROHM Semiconductor's gate drivers for GaN. These 2 single-channel gate driver products are optimized for GaN systems applications. I want to call your attention to a few key specifications on this slide that are highlighted in blue. First is the 3 nanosecond typical propagation delay. This improves overall system efficiency. Secondly, the small 6-pin package minimizes your board space. The -LB product variant has long-term product support from ROHM, making it excellent for your industrial applications. The -C product variant is AEC Q100 Grade 1 qualified for automotive applications, so you can select the variant that is most suited to your applications. Now let's take a detailed look at the technology inside these gate drivers. In this circuit schematic, you can see that there are 2 transistors on the high side, one NMOS and one PMOS. These 2 transistors provide a 2-step turn-on. The NFET provides faster switching due to its lower impedance. The drain voltage is monitored by a detection circuit, and once that drain voltage is low enough to indicate the GaN transistor has turned on sufficiently, the PFET then takes over. The PFET pulls the gate signal to the power supply rail and reduces overshoot. If you only use an N-channel device, there will be more ringing, and the gate voltage will not get all the way to 5 volts. The higher impedance of the PFET causes the voltage to rise more slowly at the very end, which reduces the overshoot. The switching image in the lower right corner demonstrates how both the gate voltage and the on resistance respond during the 2-step turn-on sequence. Here we are comparing the ROHM BD2311 NVX gate driver on the left to one of our competitors' gate drivers on the right. I want to draw your attention to the light blue waveforms. These are the voltages on the gates. For the ROHM gate driver in the left figure, there's minimal ringing, and the gate voltage never exceeds 6 volts. For the competitor's device, you can see that there's a lot more ringing. In addition, the gate voltage reaches 6.64 volts. This is over 10% higher than the gate voltage for the ROHM gate driver. And if you recall our earlier discussion, this could lead to gate breakdown for existing GaN devices that are limited to only 6 volts. We now change our attention from the single-channel gate drivers to our half-bridge gate driver optimized for GaN transistors. Providing 2 drivers inside a single package reduces your system footprint. This is an industrial-grade half-bridge gate driver that provides an excellent 16 nanosecond typical propagation delay. At ROHM, we have designed this to prevent the high-side bootstrap capacitor from overcharging by synchronizing operation with the low-side gate. Now, let's take a look at the advantages of using the ROHM half-bridge gate driver IC with our EcoGaN power transistors. Here we look at the design of a 48 to 12 volt DC to DC buck converter. In the graph at the bottom left, the silicon solution is limited to switching frequencies below 1 MHz. You can see in the red curve, the silicon solution quickly reaches thermal limits at 1 MHz. Moving over to the right graph, the ROHM system solution allows switching frequencies up to 2 MHz at very high efficiency. Now, if you look at these efficiency curves, you might think, why do I care? If I can get the same performance and efficiency as silicon, does the switching frequency really matter? So let's look at the next slide and see that it does. The answer is absolutely yes. Switching frequency matters. Here we see the advantage of higher switching frequencies. The higher switching frequency allows us to use smaller passive components. The GaN solution provides a 91% reduction in area and a 94% reduction in volume. This means more functionality in a much smaller form factor with improved energy density. Don't let the pictures here fool you. Notice the two x-axis dimensions are different. 40 by 40 millimeters on the left and 12 by 12 millimeters on the right. We have not really scaled down the EcoGaN solution as much as reality. It's just hard to show a 94% volume reduction and still be able to see the components. As systems continue to integrate more functionality into ever smaller spaces, the reduced volume and improved energy density are vitally important. Continuing our walk through ROHM's low voltage GaN products, we now turn our attention to the controllers. The BD9JZ01MUF 100 volt DC to DC controller combines a controller and a half bridge gate driver into a single package. As shown in the application circuit, it allows the creation of a DC to DC buck converter with only a few external components. With the ROHM nanopulse control technology, it supports a minimum on-pulse width of 2 nanoseconds. An external resistor can be used for setting the switching frequency from 200 kHz up to 3 MHz. This controller provides a full set of protections: overcurrent, thermal shutdown, overvoltage, and undervoltage lockout. The high efficiency and high power density of this 100 volt DC to DC controller make it suitable for a number of applications, including high current industrial applications, telecom, and data center systems. ROHM's nanopulse control enables the world's shortest turn-on time of 5 nanoseconds. As shown at left, this is significantly shorter than our competitors. With this very narrow pulse, it is now possible to build a high step-down ratio converter as shown at right. In a conventional design using silicon technology, it takes 2 converter stages to go from 48 volts to 1.8 volts with an intermediate voltage of 12 volts. With nanopulse control and GaN devices, we can eliminate the intermediate bus voltage and go directly from 48 all the way down to 1.8 volts. That means fewer parts, reduced area, and increased system power density. Here we have a demonstration example of this 48 to 1.8 volt step-down conversion. This design can provide efficiency that meets or even exceeds that of a typical 2-step DC to DC down conversion, but in a much smaller form factor and with higher power density. The circuit board shown in the upper right is a demonstration circuit, but stay tuned for an evaluation board that will allow you to test out this system and speed your development of applications that could take advantage of ROHM's nanopulse control. Continuing our look at 48 volt direct conversion, this slide demonstrates the enormous area and volume savings that are possible. With the higher switching frequency and the direct conversion, the ROHM nanopulse control plus EcoGaN solution reduces the area by 85%. And the volume by 98%, with a power density of 37 watts per centimeter squared. Nearly all the products we have been discussing so far are available today as development samples, and about half can be obtained in commercial samples, and some are already in mass production. As you can see from this table, you can begin complete system development today with all the products scheduled to move into mass production either later this year or in 2024. Before we move to ROHM's high voltage GaN solution, let's take a brief look at a couple of evaluation board examples using our low voltage GaN products. This LiDAR evaluation board uses 3 key ROHM products: the gate driver, the EcoGaN power transistor, and the laser diode, which we haven't talked about yet today. And it is targeted for applications in which the laser diode is being modulated with a square wave. It is available today at ROHM's website to help you get started with your LiDAR application development. This LiDAR evaluation board is similar, but uses a different ROHM laser diode and is targeted at resonant wave applications. These are just 2 examples of the types of evaluation boards that we have developed to help you accelerate your product development process. Near the end of today's presentation, I will introduce a couple other low voltage GaN eval boards, but I would also encourage you to check out our website to learn more about these eval boards and see what else we have available to help you accelerate your time to market. Before we leave our discussion of ROHM's total solution set for low voltage GaN products, I wanted to share this product roadmap. As you can see, we are continuing to rapidly expand our product lines. This includes adding multiple voltage options for the EcoGaN power transistors, new generations of our EcoGaN devices, new advanced package solutions such as the dual cool package with top and bottom side cooling. How cool is that? Complete modules, gate driver ICs, and even more controllers with our nanopulse control technology. Now we're going to take a detailed look at ROHM Semiconductor's 650 volt high voltage GaN products. Since we just finished talking about the low voltage products roadmap and they are still fresh in our minds, I wanted to start this section of the presentation looking at the high voltage roadmaps. Here you can see our plan for the expansion of our 650 volt GaN discrete HEMT product line. The first two products in this new family are transistors with 70 and 150 milliohms on resistance in the DFN package. These were recently announced in our global launch and are ready for mass production today. Next up across that top row is another 150 milliohm version in a different DFN package. Moving down to rows 2 and 3, you can see that ROHM will soon be releasing devices in the toll package for improved heat dissipation. Looking further out, we plan to expand to additional package options, including the DFN 5060 and dual-side cooling. Keep an eye out for a 20 milliohm version for the highest power applications, and finally, we will be launching automotive-grade versions in the coming years. Here we have some of the key specifications for the ROHM family of 650 volt GaN transistors. These are enhancement mode, normally off devices. These include a built-in ESD diode, fast switching, and zero reverse recovery. We currently have two options with on resistance of 70 and 150 milliohms as I highlighted on the last slide. In our plan is a version that is pin and package compatible with our competitors' devices, but will provide superior performance for easy replacement to quickly upgrade your system. Now let's take a look at a few other metrics versus our competitors. The graph at left demonstrates the improved efficiency of the ROHM 650 volt discrete GaN transistor shown with the yellow lines. The turn-on energy loss is reduced by 10% and the turn-off energy loss is reduced by 60%. On the right graph, the increased turn-on switching speed of the ROHM device is demonstrated. Here we are measuring the change in the drain source voltage during turn-on, where the output is switching from a high value to a low value. Thus, we want a large negative value for the switching speed. The ROHM GaN performance is again shown with the yellow line and is clearly far superior to our competitors. Now I want to introduce another exciting GaN product offering from ROHM, our system in package. In addition to expanding our lineup of 650 volt discrete transistors, we are actively developing system in package products. Across this roadmap, you can see a wide variety of solutions. The leftmost on this chart is a power stage with the gate driver integrated with the 650 volt GaN transistor. Just to the right of that is a half-bridge power stage that includes two GaN transistors. There are also several SIP designs, like the QR flyback design under development in that top row, that will include everything: the controller, the gate driver, and the 650 volt GaN transistor in a single package. These SIP products will simplify your designs, allow you to design smaller, more efficient products, improve your system reliability, and even simplify your supply chain with single components replacing a number of different products. This slide contains a lot of the key specifications for two of our 650 volt GaN power stage SIPs. Each combines a gate driver with the GaN power transistor into a single, compact 8mm by 8mm by 1mm package. That image at right lets you look inside the package to see the gate driver, the GaN power transistor, and some of those wire bond connections. There are too many specifications here to cover them all today, but I do want to draw your attention to a couple. First is the wide input voltage range of 2.5 to 30 volts. Secondly, take a look at that low propagation delay of only 15 nanoseconds. And third, the low VDD quiescent current of just 150 microamps. Now these SIPs are available in two on-state resistance values, 70 and 150 milliohms, and they are ideal for power modules, inverters, and much more. Over the next 3 slides, I'm going to provide a side-by-side comparison to one of our competitors to demonstrate the advantages of the ROHM 650 volt GaN power stage SIP. We are comparing two designs for a 100 watt, 100 kilohertz fixed frequency flyback converter. As shown in the circuit diagrams, the ROHM design using the system in package with integrated gate driver and power transistor uses 8 fewer components. And as demonstrated by the system photos, ROHM is packing more functionality into the same VQFN package. Looking in more detail at the reduction in parts, the total bill of materials is reduced from 26 parts to only 18. That's a 31% reduction. This includes eliminating the inductors required for the buck boost use case. In addition, the competitor's solution requires resistors and Zener diodes in the power and gate drive signal paths, which reduces those voltage ranges. The ROHM design therefore provides better performance while using fewer parts. On this slide, we take a deeper dive into the performance advantages of the ROHM SiP power stage. First, in the upper left, we can see that ROHM system in package reduces switching loss by 20%. This is due to the lower gate charge. Lower switching losses also mean better thermal performance. Secondly, in the lower left, we have shown that the ROHM SiP provides a 25% increase in the maximum output power. And finally, on the right side, you can see that the switching speed is 27% faster. On the top is a competitor's product, which has an 11.7 nanosecond rise time. On the bottom is the ROHM response with an 8.5 nanosecond switching time. To summarize, the ROHM system in package power stage requires fewer parts and provides better performance across multiple metrics, including switching speed, size, power output, and efficiency. As we near the end of today's presentation, I want to finish with a quick look into the sample and production schedule for our 650 volt GaN products, and then look at some more evaluation boards, both for our 150 volt and 650 volt GaN product lines. As you can see here, we are already sampling several of the 650 volt products that we have discussed today, including both the EcoGaN discrete transistors and the system in package power stage module. Volume production for these parts is scheduled to begin later in 2023 and into 2024. At ROHM, we are ready to help you get started designing these products into your new system, so reach out to us to acquire samples or get design support. We talked earlier about a couple of LiDAR evaluation boards for the 150 volt GaN product line. Here we've added a few other of the low voltage eval boards, a half bridge, a buck converter, and a boost converter. All of these are available today and have the supporting documentation you need to accelerate your product development, your testing, and your validation. In addition, here we have two evaluation boards available in support of our 650 volt high voltage GaN products. The first is a 100 watt quasi-resonant AC to DC converter. The second is a 240 watt boundary conduction mode boost power factor correction converter. And as you have seen from our product roadmaps and production schedules, there's always something new at ROHM. So keep an eye out for more eval boards just like these. Thank you for your time today and your interest in ROHM Semiconductor's low voltage and high voltage GaN products. If you'd like to learn more, please head over to our website at rohm.com. You can find data sheets, application notes, product information, and contact information if you'd like to speak with our experts who are ready to help you build electronics for the future. Thank you.